In this video, we're going to talk about weather models, how they work, and some of the different types of weather models meteorologists use daily. We're also going to talk about universal time, or Z-time as it's called in the weather community, because understanding the timestamps on these weather models will be crucial for when you forecast down the road. But first, what is a weather model? A weather model is a tool used by meteorologists in order to predict the future state of the atmosphere. There's a dozen of different weather models out there, each built slightly different from the other and built for different purposes. Some models focus on large-scale circulations of the atmosphere that are used for seasonal or long-term forecasting, while others focus on a more medium or short-range time span, like weeks, days, or even hours. Weather models are dependent upon atmospheric data. They take current weather observations and use that data to import them into these supercomputers that house the models, which then begin solving thousands of lines of equations that look like this and this. Meteorologists and computer scientists then take those complex equations and write them in code, which the computer can then understand. Eventually, the weather model finishes solving all those complex equations and outputs a result. The results are then overlaid on a map, which is more visually appealing to the forecaster, so he or she can then analyze the results and therefore make a prediction. Since the results a weather model produces depends on the data going into it, oftentimes bad data will get ingested into the model and will then therefore produce an off result. It's then up to the forecaster to decipher which model looks to be more correct, which is also why we have a variety of weather models to choose from. Now, this is a skill I will teach you down the road. Now, how do we collect data? While it's easy to measure things like temperature, humidity, and wind speed here at the surface, weather balloons are used to measure similar parameters aloft. Weather balloons are launched at the same time around the world twice daily, both at noon and midnight, Greenwich Mean Time. Attached to these weather balloons are instruments called radiosondes. Radiosondes also measure temperature, humidity, wind speed, direction, and a few other key atmospheric elements just high up in the atmosphere. Those measurements are then transmitted back to the weather models that then begin solving those complex equations. The measurements give models key information on the current state of the atmosphere, so the model can therefore more accurately predict what might happen later. Each dot on this map shows where a weather balloon is launched. While there are a good chunk of locations that launch weather balloons, there's still a decent chunk of the atmosphere that isn't measured, simply because it's impossible for humans to measure every single inch of the atmosphere, which is why weather models sometimes produce bad results. Now I want to talk about the three main weather models that you will see often throughout this course. The first one is the NAM, which stands for the North American model. It's an American-made model, and it's more a short-range model, which means it only forecasts out 84 hours, which is only about 3.5 days. There's different versions of the NAM. As I like to call them, they're the NAM's first cousins. One of those cousins is the HRRR, or the High Resolution Rapid Refresh. This is a very short-range model that forecasts out only to about 14 hours. While the NAM runs 4 times a day, the HRRR will update every hour. Other versions of NAM are called the WRF, which is used for research purposes. There's also what's called the RPM, which is more commonly used on TV, especially when they show the futurecast of weather radar. The second weather model that we use often is called the GFS. It stands for the Global Forecasting System. This is a medium-range model that will forecast out to 384 hours, which is about 2 weeks. And this also runs 4 times a day, and it's also an American-made model. Now, to compete with the GFS, we have what's called the European model, or the ECMWF, which stands for the European Center for Medium-Range Weather Forecasting. It's also a medium-range model, but that only forecasts out to 240 hours, which is about a week and a half. Now, statistically, it's the better of the three models, as in it gets more forecasts correct. However, the GFS does have its days where it will outperform the European model. Not always, but there are some times. The NAM is used better or best for short-range forecasting within the next 1 to 2 days. But it's also important to note that the European also runs twice a day, whereas the American models will run 4 times a day. Now, it's a little bit of a joke in the weather community if you take the 3 models and you put them side by side and you act like as if they were students taking a test. The European is the brainiac child. It's the one that gets the most forecasts correct. The GFS, like I said, does have its days. However, it tends to copy off the European. Oftentimes, as an operational forecaster, I have seen the European lock on to storms quicker than the GFS, meaning that the European will show that there is a possible, let's say, snowstorm in the Northeast a week out, and then the GFS will show that same system only a couple of days later. So it's almost like the GFS copies off the European, but sometimes those roles are reversed. Now, the NAM is kind of looked at as the student who has no idea and picks its nose. But that's more along the lines of if you're using the NAM for predicting the weather 3 to 4 days out. The NAM is best when you use it when the event that you're forecasting for is within a 24 to 48 hour window. And so the NAM, even though it's not a bad model, it does tend to be a little bit more awry, especially when it tries to forecast 3 to 4 days out.